Good, thank you. Welcome to the last lecture. After this, we have the exam. The exam is going to be on Friday of this week at 9 o'clock in the morning in the same room that we had our midterm in. So I hope that all of you will, study up, study hard, because the exam is the exam. For some people, particularly those who MSAF the midterm, the exam is worth 70% of the final grade, and there is an option for having the exam worth up to 55% of your final grade. If you fare better on the exam than the midterm, then sufficiently better for the math to work out, then half of the grades from the midterm will be allocated to the final exam. So, if you didn't do well on the midterm, you have an opportunity to redeem yourself on the final. Good. Do we have any questions before we resume our lecture from yesterday? I should probably wear the mic. Always forget the last thing. Question? I would say talk to the TAs directly, like via email. They'd be happy to help you out rather than, because the timeline's a bit tight, we can't do public discussions. But you can definitely talk to the TAs individually about that. Okay. Test. 1, 2, 3. Good. Excellent. So, last time we were talking about machine learning and how it is not going to cause the apocalypse. It is simply a statistical tool, like many other statistical tools that we have developed over the course of human history. We did an introduction to various different styles of machine learning. We talked about regression analysis, we talked about clustering analysis, we talked about what a feature vector is and how to calculate the distances between them. Now we're on to linear regression. So linear regression is a very, shall we say, common topic in statistics. It's entirely likely that you would have seen this in high school, but we're going to talk about it anyway. So, we had covered the basics of what linear regression is and how one goes about calculating the goodness of fit of a regression line. Now, we're going to see an application of this using Python itself. So, the library that is recommended for use on linear regressions is Scikit Learn. This library contains a number of the machine learning modules which are so popular these days among researchers. This package comes pre-installed in the Anaconda distribution, which a lot of you, I'm sure, have. It is also being installed on JupyterHub. That's a different JupyterHub than the one we're using, but the one we're using is a clone of that older one, so everything still applies. To install on your local computer for use in your own local installation, any of the following installation lines will do, depending on your operating system and what your package manager is. At any rate, the easiest way is to just download Anaconda. Basically, if these commands don't mean anything to you, install Anaconda. So, our procedure for linear regression just to recap. Number one, we must obtain the data itself, obviously, otherwise what are you calculating the linear regression of? Number two, we divide the data into two sets, a training set and a testing set. Three, we run a regression analysis on the training data to get a proposed coefficient and intercept. Four, we use the proposed coefficient and intercept to predict the y values of the testing data from its x values. We then measure how far the predicted y values are from the real y values in the testing data to determine the goodness of fit. It is not sufficient to have simply developed a model. It is also you also have to test that model to ensure its validity and accuracy to reality. Good. So, to obtain the data, of course, depending on what your field is, you might be performing experiments, you might be taking measurements, you might be collecting data from the internet or any number of things. In our particular case, we generate random sample data with a function in Python. This is just so that we can save the step of having to go out and find real data. At any rate, in order to perform a two-dimensional linear regression, it is required that your data be in the form of x, y points or coordinates. You need an x dimension and a y dimension. So let's go through this code very quickly. So first of all, we're importing the random library, which is something we haven't seen yet, but that's how you generate random numbers. Generate sample data takes the coefficient and number of samples and the y spread, and essentially just for loops over a range from 0 to the number of samples, right? So that loops once for each sample that we're taking. We calculate a y value as the rounding of the coefficient times x plus the y spread times a random factor. So essentially, let me explain how random numbers work in software. First of all, computers are not capable of true randomness. A computer is a completely and wholly deterministic system. So it's not possible for a computer to just think up like the number 7, to pick a random example, so to speak. So what happens, the way that computers actually generate random numbers, there will be some complicated calculation which scrambles another number, essentially producing a random number from the first number. But you always require that first number in order to produce the second, right? Anybody here play Minecraft or have played Minecraft at some point? In world generation, you have the option of including a seed value, right? That seed value is the random number, or it's the number from which the random numbers that generate the world are derived, right? So generally, when you're working with a random seed, what you want to do is, like, every time you need a new random number, you increment or perform some, you add 1 to the original number that you're using as a seed, and then you get, if you've got a good scrambling algorithm, you get what looks like a completely random number each time you do that, right? So that's why providing a single random seed allows you to regenerate a Minecraft world that was previously generated, right? So that's how some video games will do that for world generation, just for like a repeatability thing. It's easier to test the game while it's in development if you can ask it to generate the same world under the same conditions multiple times, right? The way that programming languages like Python will handle things like their random library rather than asking for a seed value, notice that no argument has been provided, it will default to something, some value within your system that is like frequently changed. For example, the current time and date in like microseconds. So long as you're not requesting a new random number, you know, multiple times per microsecond, each random value that you come up with will be different because the time will have moved since the last request, right? So that's essentially how randomness works inside of a computer system. Ordinarily, you've got two main variations of random number generation. You can generate, well, three. There are three main ways of generating random numbers using something like the random library. You can generate a random number within a range of integers, right? You can generate a random number, floating point number, between 0 and 1. And if you take a random number between 0 and 1 and perform some kind of mathematical operations on it, then you can essentially get a random floating point number for any range, right? The subtract 0.5 here, basically, you know, if we were generating these points, right, without that 0.5, all of the points that we would be generating would be within a certain distance above the line, right? By subtracting by 0.5, we effectively move that range down, you know, we move it so that it hugs the line a bit better, right? And the spread, of course, is the multiplicative factor y spread that determines how long the interval in which the random numbers will be generated will be. Make sense? So that's a little bit of a diatribe on randomness. So essentially, what we're doing here, given the x values, we just generate a bunch of y points. We then append those pairs to the data set. So this is like, you know, essentially what we're doing here is like for every value between 0 and whatever, however many samples you want, we're generating one like y value with a random range around the line of regression that we're trying to reconstruct. So essentially the way that this example will work, we have a true function, right, which is used to generate the random samples. The goodness of fit, or the degree to which we are able to reconstruct the original coefficient that we've, you know, that we've asked for here, will tell us, you know, how well our regression is done. Notice that we are not introducing the idea of a, what do you want to say, a y-intercept here. There's no like constant factor. So you could easily modify this function to take in not only a coefficient but also an intersect. You just add another parameter here and add it to y, right? But in this case, they're not doing that. So in theory, the line of regression should pass through the origin or very close to it. Make sense? Any questions? Good. So, step 2 is to divide the data into two sets, the training set and the testing set. So, the best practice is to try to split this as evenly as possible. So, yes. Of course, you can't use the training data as the testing data, because no matter what model the computer comes up with, it will hypothetically predict the data with which it was trained perfectly, right? What you're interested in is data outside of the scope of the data that was used to train the system, right? So that's why we have to split the data. So there are, so in this case, we have a function which splits the testing data, the testing and the training data, right? What we're doing, we are inputting the data, we are declaring what the proportion is, right? And essentially, we set we're using the indices here in order to declare which of these two, is this going in one or the other, basically. So the method that's being used here, we generate out all of the indices which are going to end up in the training data, and all of the rest of the indices are going to be dumped into the testing data, right? So, like, you might be asking, okay, that seems like a complicated way of splitting it. Why wouldn't you just split it down the middle, right? Well, it turns out that data can sometimes be susceptible to positional bias. So if you have a series of measurements, it is entirely possible that, for example, the human making those measurements becomes more efficient at making the measurements over time, right? So the first, 10 measurements, you might be, biased towards the reaction time of the person doing the measurement or some other such, qualifying factor, shall we say. If you were to take the data and just split it down the middle, send it to one side, send it to the other, then the training data would include all of those trials effectively that trained the human doing the testing, right? So they may not come up with a representative look at the data. In the same way, taking the, you might say, okay, sure, we can't just split it down the middle, but why can't we just alternate, right? 1, 2, 1, 2, 1, 2. Divide it up like that. If you divide it up periodically, then you're susceptible to periodic biases as well, right? So let's say that the machine that you're using to make the measurements, like every fourth trial takes just a little bit longer for whatever reason, right? It skews every fourth data point that it's measuring, right? If you were to then split the data according to regular intervals, all of those skewed data would end up in one set or the other. The goal is to divide them up between the two sets evenly. So, if the means by which you divide the sets up is random, what you're effectively doing is you're introducing a large number of different sampling frequencies into the data, right? Any bias that occurs along a particular sampling frequency is not going to be, it's not going to be susceptible to that because there are many different frequencies of the data. This is kind of signal processing stuff as well, which is probably beyond the scope of this class, but we have time actually if you're interested. Are you guys interested in signal processing? Anybody here has anybody heard of the Fourier Transform? Okay, this is like not 1MD3 stuff, but you might find it interesting. So, radio, right? There are two major ways that radio is transmitted, right? AM radio, FM radio. Do you guys know what AM and FM stand for? AM stands for amplitude modulation, frequencies, and FM stands for frequency modulation, right? So with AM radio, basically the idea was to transmit the sound wave as nearly as exactly as possible through radio wave, right? So you have a signal that carries its information in the amplitude of the waveform, right? With frequency modulation, the information is stored in the frequency of the waveform rather than the amplitude. So it's like it'll have a close section, longer, closer, closer, longer, longer, like that. The amplitude of the frequency modulated signal remains relatively constant. So this is the reason that AM radio sucks and FM radio is good and much more clear, right? It's because, like, there are regulations. You can only make this signal so strong, right? So the peak here, right? That's the limiting factor. You can only pump out so much power in these radio wave amplitudes. The frequency modulated can use the full amplitude to transmit any data, right? Amplitude, like when a radio wave passes through a solid object, it's the amplitude that takes a hit, not the frequency. Which is why FM radio is much better, like, inside of buildings, for example, because the building itself, like, while it might knock down the amplitude of the signal, that's not where the information is being carried, right? So far as it goes. So essentially, the idea is there's a mathematical transformation that you can apply to periodic signals called the Fourier Transform, right? The Fourier Transform takes a periodic signal and, let me just close. It takes a periodic signal and breaks it down in terms of sinusoids of varying frequencies. And it's possible to reconstruct signals imperfectly, but usually pretty well, by just knowing the amplitudes of the various frequency components of that signal. I have some slides on this in another course I'm going to pull up. I promise I won't talk about this too much, but you know. Yes, there we go. So essentially, right, let's imagine you have like a signal that's like a square wave, right? You can come to nearer and nearer approximations of a square wave by adding together sinusoidal signals with various offsets and amplitudes, right? The more of these components that you add, the closer you get to a perfect square wave. You'll never be able to achieve it perfectly, but you can come close enough that you can, for example, deceive the human senses. So this is what it means to, like, encode information inside of frequencies, right? Various, like, when the frequencies carry sort of information, this is the type of information that you carry. It's, you know, you can construct all kinds of different waveforms using these sinusoids. You know, you can use triangle waves, square waves, sawtooth waves, anything you want, right? The only trick is that it has to be periodic. So it turns out that this is actually how the human ear works. The way that the human ear actually works is you have this long spiraling chamber that's got all kinds of little hairs inside of it. The frequencies that you hear are transmitted through the ear canal into this membrane here, which vibrates the fluid inside of the inner ear, right? The vibrations of the vibrations of this fluid are sort of amplified by the continual narrowing of the tube, right? So what happens is that a sound at a particular frequency will activate a particular patch of hairs on the inside of the inner ear. So in effect, what this thing is it's a biological implementation of a Fourier transform, which is really cool, right? So, yeah, and frequency analysis can yield lots of interesting information as well. This is a breakdown of the frequency analysis of the voices of, on average, of males, females, and children. Like, human voice contains many, many frequencies in it, right? It's not like a sound of only a single frequency that distinguishes the male voice from the voice of females and prepubescent children is the fact that you've got these lower frequency ranges filled out. That's why men have deeper voices. Like, men have the frequency components roughly overlap those of females, right? Like the male voice contains as many high frequency range waves as a female or a child. The difference is that this lower bit has been filled out as well. So, yeah, but anyway, so that's like basically what these plots are, is you take all of the frequency of all of these sinusoids and plot the amplitudes of the human voice at all of these different, break it into its sinusoidal components and plot their frequencies, or plot their amplitudes. But yeah, anyway, so there you go. Yeah. You'll notice that pretty much everybody, when they're shouting, they gain more in high frequency ranges than in low. So, but yeah, anyway, that's science. I don't want to talk about that too long. I just thought that was interesting and we touched on it. So, and we have some time. So, anyway, so basically, the point that I was working towards is when you're dividing up the data, information can occur periodically. So if you choose something that's random, right? It's like noise, white noise, like static in the radio. Noise can be very useful as a means of dividing things in a way that is not susceptible to any content that might be in the frequency. So that's why you do it that way. Hoo-ha! So, so we can then generate the data, and then if you plot the data, you get something like this. And this is just a plot like we did during the visualization section of this course. So far, so good. Now we come to the part where we actually perform the regression analysis. So from Scikit Learn import linear model, we create a regression object by constructing it, linear model dot linear regression. We then convert our X training data to a fixed 1D array, which is basically, that's an extra step that you have to do that we don't really have sufficient background yet in Python programming to explain why you have to do it, so just do it. And then we call regression.fit with the x training and y training data. The fit method stores the coefficient and intercept that it generates from that data in the object itself. You can access it with regression.coefficient and regression.intercept. So, Scikit Learn expects that we are doing complicated data sets in high dimensions. Unfortunately, we have to do an extra step to convert a basic 2D regression using the function below. So basically, you have to squeeze the data back down into a one-dimensional array in order for this to work. So it goes. So, using the proposed coefficient and intercept to predict the y values of the testing data from its x values is quite simple. Regression.predict tells you what the y prediction would be for any particular x position. Of course, it also expects one of these one-dimensional arrays. So we generate our testing x positions by extracting the first element of the testing data set. We do the same for the y testing values. We then generate y predictions and y tests by predicting y from the x test values. So it's very important that this is the same as that, right? When we do this, we always want to be predicting the same points as were actually in the testing data. So we can then plot the testing data as a scatter plot. We can also plot the predicted data as a regular plot, and you can see the predicted data, of course, lies perfectly along the regression line. So this is essentially, if you take the distance between each of these points and this line, that's how you come up with your r-squared coefficient. If you weren't at a computer that has Python, which already can calculate it for you. So, remember, for mean squared error, smaller is better, and for r squared score closer to 1 is better. So, all we have to do is from Scikit sklearn.metrics import mean squared error and r squared score. All we have to do is plug our testing and predicted values into both mean squared error or r squared score, format and print the results, and bing, bang, boom. Any questions? So you can perform regression models on multi-dimensional data as well. So in two-dimensional space, our linear model becomes c times x plus b, right? Or mx plus b, if you prefer the high school version. Anybody here done linear algebra? A little bit? A little bit? What does this describe? What does this equation describe?
I think it describes. Okay, wait.
Say again? Nope. It describes a plane in three-dimensional space, right? So the regression model will come up with something that is one dimension less than whatever the dimensionality of the thing you're currently working in is, right? So when we are working in two-dimensional space, we come up with a one-dimensional object which traces through two-dimensional space, i.e. a line. when we are dealing with three-dimensional space, we produce a two-dimensional object which finds its way through that three-dimensional space, i.e. a plane. When, of course, we are dealing with n-dimensional, when we're dealing with n-dimensional data, we come up with an n-1 dimensional model of that data through regression analysis. So, if the dimensionality of the data is 4, then the thing that would be produced is a volume, right? A volume in a three-dimensional volume expressed in four-dimensional space, which of course doesn't quite exist in classical physics, but that's part of the fun of math, is that you don't have to worry about such pedestrian concerns as can that actually exist. So, for example, if I were to take a data set expressed in 3 dimensions, roughly the same procedure, but extended by one more dimension, right? We've got x, we've got y, and we've got z. The regression analysis of this data would predict a plane, which you can still find distances to in any way that you would be interested in. Yeah. Any questions?
So, let's say it was for 4 dimensions.
Yes.
So then what would the output be?
Well, you wouldn't be able to plot it, right? It's not like the plotting of points in 4-dimensional space is not something that is in accordance with standard geometry. There are a couple of different ways that you can plot 4 dimensions. One, you can map it to time, so you can have an animation, right? So you could see a volume grow and contract over time. You can also express that as you could say, have a series of images, right? That's, you kind of imagine laminating all of those images together. You could, do it on the same plot, but do it concentrically in some way that, makes sense, but, and this is just assuming that it's something relatively simple like a sphere that you can do that with in your mind. If you want to if you want to plot 4-dimensional space, your options become somewhat limited to make it intelligible, and don't even talk about 5th-dimensional space. Whereas in 4th dimension, you require a series of progressing graphs. In 5th-dimensional space, you need a square of the same, right? And if you were to do 6th-dimensional space, you would have to have a cube of these graphs, right? And then by the time you hit 7th-dimensional space, you would have to animate those because you've hit the 3-dimensional limit again of physical reality. It gets complicated. Basically, the way to do this is to think in terms of pure math and not with respect to visualizations, although visualizations are very useful. Yeah, does that answer your question? Can I recommend a video game? If you haven't played Fez is a game that's very interested in dimensionality, and it's very cool. if you look, you can. It's like a playable mathematical world. It's very cool. Anyway. Yes. Anyway, so let's move on and talk about classification. So we were talking about classification earlier, sort of in general. Now we're going to see some of the finer details. Classification is usually a type of supervised learning. There are two or more classes or labels. The goal is to come up with a rule that classifies inputs based on the classes in the training data. So we are trying to examine pictures and determine whether they contain a dog or a cat, that type of thing. So, using our example data set from earlier, column A contains the names of all of the things, which is largely irrelevant. Columns 2 to 6 contain the features. So 2, 3, 4, 5, 6, these are the features. And in this case, the classification that we're trying to come up with is this, does this data represent an animal, or a reptile, or some other type of animal? Now, you might look at this and think, oh, this is fairly skewed data, and you're right. Training the computer on this data will give the computer the strong impression that having no limbs is a fairly strong factor in being a reptile. But, that being said, having scales matches up perfectly. So, so, good. So, of course, our initial set of steps is very similar to what we saw before. We must convert each animal's features into a feature vector with some value representing each feature. For our animals, we get the following feature vectors. We're using trues and falses now instead of zeros and ones, which is fine. Our classification procedure. Number 1, obtain the labeled data. Number 2, construct feature vectors for the labeled data. Number 3, divide the data into two sets, the training set and the testing set. This should sound familiar. Train the classifier on the training data to develop a model. Use the classifier to predict the labels for the testing data and measure the accuracy of the predicted labels on the testing data. So it's basically the same procedure as with linear regression. The only thing we've done is we've swapped out the type of model that we're expecting the computer to produce, and we are using higher dimensional data, right? In this case, the dimensionality of the data that we're working with is 5. So, obviously a simple linear regression would not be applicable in this case. It just is the wrong type of data for it. So, a brief note on the measurement of the accuracy of data. So, and this is probably terminology that you would come across more frequently in medical literature. But this is generally how the validity of tests is described. So basically, when you test something, you are trying to predict the true value of that thing, right? Take, for example, the COVID, right? You can take a COVID test that might give you some indication of whether or not you actually have COVID, right? But it's not perfect, right? The test does not predict with 100% accuracy. Another way of saying that is that not all positive tests indicate, not all positive tests indicate a positive, how would you want to say, state of reality, and not all negative tests indicate a negative state of reality. You can take a COVID test, get a positive result, and you can still have, and still not have COVID, right? Now, the validity of the test generally is determined on things like what is the percentage with which, you know, things deviate from these two categories. You know, if I were to take 10,000 tests, how many of them would be true positives or true negatives, and how many of them would be false positives and false negatives? If a test has a very high false negative rate or false positive rate, we generally consider it to be not a very good test. You can increase the probability of that test being accurate by taking more tests, but that's assuming that the factor which caused it to be falsely positive or falsely negative has gone away in the intervening time. So, you know, just to take a random example, if you were to take a test for a virus like COVID, and there was another virus in the environment which was, you know, highly similar in terms of its structure to COVID, enough to fool the test, shall we say, and if we also assume that that virus is like one of the benign ones that doesn't cause symptoms, so you're not like, you know, having visible symptoms of any kind of respiratory illness, then, you know, taking the test, you know, 3 days apart, if you still have that other virus that's fooling the test, is going to result in multiple false positives because the factor that's throwing it off hasn't gone away, right? So anyway, you know, I think everybody knows this already, but if the test correctly predicts it to be the thing that it is, it's either a true positive or a true negative, depending on whether the test came out positive or negative. And if the test incorrectly predicts reality, then we are talking about false positives or false negatives. Generally, the preference is for false positives rather than false negatives because, you know, as long as whatever you do in the case of a false positive isn't too invasive, missing, for example, cancer has more impact than incorrectly finding it, right? Normally, you know, the thing you want to do in any case is to do more testing. There's like you can never have too many tests, essentially. Yeah, the more testing you do, the more accurate your situation is. But anyway, you know, the more testing you do, the more accurate the situation is, assuming that the testing that you're doing isn't crap, right? Like if you had something with like a 95% false positive rate, then you shouldn't be using the test. But anyway. So anyway, for classification in Python, we use the Natural Language Toolkit, which is it's an interesting one. It contains a lot of fun little bits and bobs. Natural language is a computer programmer's way of designating all languages that are not computer languages. Because, you know, programmers like to think in programming languages as much as possible, and to soil their hands with the pedestrian, you know, proletariat masses of people who speak, you know, spoken language. They like to keep as much distance from that as possible. And who can blame them, because natural languages are terrible. Ask anyone who speaks one. Natural language is a particularly thorny issue for computer scientists. Artificial intelligence research originally meant trying to do something with human languages. AI is a very interesting field because basically it's like a bunch of like people trying to do really advanced stuff. They have partial success in some field, and then whatever they have success in, like spins off and becomes its own field, subdiscipline of computer science. Like a good example of this are things like speech recognition. Like all kinds of phones have speech recognition, right? Like this video that's being recorded will be subject to speech recognition software for the purposes of generating automatic captioning. Now, it takes time to do that. Basically, I don't get the captioning like immediately. It takes like 24 hours for them to process the video and put the captioning on. So that's why you don't get your captions immediately. But yeah, so like there are huge applications of you know, voice processing, speech processing. But, you know, speech processing is very, very complicated. You remember that bit that we were talking about, the human voice? It turns out that each sound that you make with your mouth has a specific frequency profile, right? So, what you have to do in order to recognize speech is you need to perform a fast-running continuous Fourier transform over the waveform that has been recorded, right? Analyze it for its frequency components, pick those out as being phonemes, phonemes being like subcomponents of words, like ka is a phoneme, stuff like that. And then, you know, you then have the problem, once you've established what phonemes are, is how the heck do you spell that in English, for example, because holy hell is English spelling complicated, right? There are phonetic languages where it's a little easier, but in general, you know, once you have phonemes, it's not trivial to get from them to a sentence, right? Another thing that's like very, very common, I think particularly in Germanic languages, is that, although, you know, Romance languages are also particularly bad at that. You notice, like, I speak like my sentence is one long word, you know? That's generally how people talk, right? Because the spaces between words they take time, and there's only so much time on this planet, and most humans are good enough at processing words that I don't have to talk like this, right? Spacing in the words can be used for emphasis rather than, you know, simple declaration of the words themselves. But of course, the problem is, to a computer, it sounds like you're saying one long word containing like, you know, 40 phonemes. Where to divide them up into words, all of these phonemes, is like also a problem. But anyway, so that's like, these are only some of the problems that were addressed, you know, back in the 80s and 90s, I'd say, by people who were you know, AI researchers who wanted to develop some way for human beings to be able to talk to the machines. It's interesting because basically we're getting there, but all of the science fiction authors that predicted that robots would have achieved like human levels of interaction with the world by this point in history severely underestimated the difficulty and complexity of the problems of, you know, the ways that human beings interact with the world, right? To try to simulate the way that human beings interact with the world, you have to like first understand how we interact with the world, right? And like this, like we have absolutely no idea what consciousness is. So trying to give consciousness to a machine is like, you know, let's just say we've got some work to do. Which is another reason why the singularity is not something to worry about. You should worry about, you know, more local concerns, I'd say. Anyway, so Natural Language Toolkit. You can install it using similar operations to previously. It's already on JHub. It might not come with Anaconda, but if you want it, you can go get it. So, step one, obtain labeled data. As we've done so far. Step two, construct feature vectors for the labeled data. For the natural language toolkit, we need a list. Each element of the list is a tuple containing two things. Number one, a dictionary of feature names and values, and a label. So, for example, with our class animal, we add a method to it which allows us to extract the feature vectors as a dictionary. So we have a set of feature names. We have we start our empty dictionary for I in range length self.features, i.e. loop over all of the features. We construct a dictionary entry using the names and the features, and then return that dictionary, right? We enter all of our data, we have all of our animals, and then our feature sets themselves is a list comprehension over animals, which just creates a tuple between this dictionary and whether or not the thing is a reptile, which is indicated inside of the class. Make sense? Good. So, what you get as a result of that, if you were to apply this, if you were to print the state of these animal objects according to the code that was just added, you see we get all of these dictionaries with all of the values being populated in them, and we have a set of true and false values, which are our labels.
I think your microphone.
Is my microphone off?
Yeah.
Hello? Hello? Hello?
Yeah.
Test, test, test. Up, 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 up. Maybe it's running out of batteries. Let me know if it happens again, eh? Thank you. So, then of course we divide the data into two sets, the training and the testing set. This should look familiar because it's the actual exact same function from earlier. We use the same method for randomness. Then we train the classifier to develop the model. So, there are many types of classifiers. In this example, we are using one called a naive Bayes classifier. So, from nltk.classify import naive Bayes classifier, our training data is our feature sets, all except the last element. In this case, we're sort of skipping the bit where we divide the data because we don't have that much data to divide. We're basically going to train the classifier on all of the data except the last entry and then see if the last entry is predicted, just because this is a small example. Classifier is nltk.naive_classifier.train training data. This returns a classifier object in which the data will be stored. So, once we've run our trainer, we can learn a little bit about the model that it's developed. So, most informative features: legs, scales, cold-blooded, and legs being equal to 4, scales being equal to true, cold-blooded being equal to true. This is the degree to which these features predict the reptilian status of the animal, which is cool. Yes?
Can you go back? So how much does, what shows the influence of each feature on the animal being a reptile?
For example, this here, right, false, true, what this is saying is that legs being equal to 4 indicates that it's not, like the ratio of false to true, right, not a reptile versus is a reptile is 2 to 1. So,
okay.
legs being 4, like, if we go back to our original data, like, if you look at those animals that were not reptiles, half of them, like 1 out of the 2 of them had 4 legs.
Yeah, the frog and the alligator. Right?
Yeah, so legs powerfully predicts.
Got it.
Right? Make sense?
Yeah.
And the same is true for the rest of them. Yeah. So. We can also use the classifier to predict the labels for testing data, as you might expect. So, we set up a list of predictions. For t in the testing data, predictions.append classifier.classify the element, the first of the elements. So remember that what we're dealing with here is a tuple. The testing data is a tuple between a dictionary and a label. In order to predict the label, we just give the dictionary, which is the first element of the tuple. Make sense? Good. So, next, we want to measure the accuracy of the predicted label on the testing data, which, again, there's a method for. nltk.classify.accuracy classifier and testing data. Boom. Total number of correct predictions versus total number of predictions. So essentially, it goes through each element in the testing data, right? Notice this is the whole testing data, including the labels, right? So it goes through each element in the testing data, makes its prediction about the first half, and then sees if it matched the second. Make sense? Good. There's so much for classification. Any questions?
So, so what does? Okay, so NLTK is a
library.
Okay.
Yeah. It's the Natural Language Toolkit.
Okay, natural language. Right.
So speaking of natural language, let's talk about sentiment analysis. This is certainly a subject that has been of some importance in social media in recent years. So, a special type of classification problem focuses on identifying the sentiment of a piece of text. So, for example, a tweet. It might be useful to you to be able to identify whether the sentiment expressed is positive or negative, happy or sad, angry or not angry, any type of sentiment you might wish to express. The basic approach is to label individual words as being associated with a sentiment, then compute a sentiment score for a particular piece of text. So this is sort of the classical approach. Very simple. It's like you go through the dictionary and you assign each word a particular, sentiment value in various categories, and then you just total those sentiment values by counting each of those in the particular sentence. The machine learning approach labels pieces of text as having a particular sentiment and then uses classification to predict the sentiment. So, whereas the basic approach requires the human being to associate, particular sentiments with particular words, this is not an a-theoretic approach. The inbuilt biases of the human being will have an effect on the outcome. It's like you might feel that the word gregarious is positive, but if the way that the Zoomers are using the word means a person of ill repute, then your prediction about what that word actually means doesn't actually correspond with reality. It's much better to be able to, derive the word meanings from their use in context, rather than, come up with some kind of a priori assumption about what the word means, because language changes and shifts frequently, even increasingly frequently during the present age, almost to the point where the dictionary is useless these days. So, the procedure for building up a machine learning sentiment analysis engine, number one, and this should be very familiar by now, obtain your labeled data, construct feature vectors for the labeled data, using natural language processing to construct the feature vectors. So rather than just simply having a bunch of variables with a bunch of values and constructing the feature vectors that way, what you have to do is you have to, use a natural language toolkit to process out the actual words of the sentence. Now, we'll talk about this a little bit later in a few slides. You, of course, divide the data into the training set and the testing set. You train the classifier on the training data. You use a classifier to predict the labels of the testing data and measure the accuracy of the predicted labels using the testing data. Same procedure. The exact same procedure, using a different analysis engine. So, the goal of natural language processing is to transform natural language into a form that is more effectively processed. The first step, generally speaking, is tokenizing. This is a term derived from parsing and compiler theory, but a token is essentially any part of speech or a sentence, right? So a word is a token, a piece of punctuation is a token, right? It's anything that's in there. That's what a token is. And tokenizing is the process of splitting the sentence up into tokens. You guys have all done tokenizing every time you've done split on space. So, we then tag, that is to say, mark tokens in a passage of text with tags representing their grammatical role. This, so basically, once you've tokenized, once you've split a sentence into words, you then look all of those words up in the dictionary to see if they're nouns, verbs, adjectives, etc. Next, we want to perform stemic, which is to say, the word happy, happier, happiness, happiest, all express the same root word. So, you can minimize the number of factors at play by taking variations on root words and recomposing them back down into the root word, right? It reduces the number of variables, which is good. Also, you remove common words that have little meaning. Things like prepositions and articles and conjunctions, right? Although these are all of these types of words are of, great importance to a natural speaker of the language, they do not carry sentiment, generally speaking. Some languages don't even have them, or some of them anyway. I'm pretty sure most languages have a word for and. But then again, I'm a computer linguist, not a natural language linguist, thank God. So, you then take all of these things and construct a feature vector for the labeled data using natural language processing. So, once you have tokenized, stemmed, and removed stop words, you then construct a list of all processed tokens present in all samples. Remember that each one of these sentences has a label. as to whether it's a positive or a negative sentiment. Which again, you know, you don't quite get to avoid the problem of human beings introducing their own biases, because in this way, the bias is introduced not at the level of the word, but at the level of the sentence, which might be an improvement, right? Human beings might fairly reliably be able to tell you whether a particular sentence is an insult or not, but they can't in the same breath because human beings are very fallible. So, we then run classification algorithms on these feature vectors to determine, you know, whether or not they are happy or sad or what have you. Vader is a sentiment analysis tool built into the natural language toolkit. It is already trained to classify passages of English texts on positive and negative sentiment. So, if you use nltk.sentiment.vader.sentiment intensity analyzer, and you give it a sentence, and you ask for the polarity scores of a particular sentence, you'll see that the sentence, if you are happy and you know it, clap your hands, is 0.7%, 0.7 neutral, 0.29 positive, and 0.57 compound. So although, you know, if you're happy and you know it, clap your hands, is generally associated to be, you know, positive, with a positive emotional valence, as it's a children's song, slash that song that was made by that other guy at one point. It was basically just, you know, because I'm happy, you know, the happy song. That's basically, if you're happy and you know it, clap your hands, redone for adults. But anyway, so yeah, you can analyze the sentiment inside of human speech. Although I think, if, you know, I would say this is still a very long way off from being the singularity. So, there we go. So, in summary, nothing else. There we go. We're done the course. Congratulations! You have finished 1MD3. The lecture component, anyway. Any questions? All right. Good. Review session start. Anybody have any review questions?
I have.
Okay. Let me, what would you like to review?
Floating point numbers. And operations in file IO.
Operations in which?
In file IO.
Oh.
The file.
Anything like just general file IO?
No, a specific thing, like in the assignment, we had to like order the dates in like sorted dates, right? We had to sort the dates. I didn't know how to do that, so that's my question.
Okay.
Yeah. And in floating point numbers, the accuracy, yeah.
Anyone else got a topic? SQL queries? Yes? Recursion. Good one.
Could we go over how to use self in
Object-oriented. Self. Yep. else? Is that good for starters? Okay, let's see. I'm going to do these in no particular order. Let's start with the back of the course and move our way up. So let's talk recursion. So, recall that a recursive function, is this thing, yeah, it's dead, eh? Let me just replace the batteries. Ugh. If the university would spring for less cheap batteries, this might not be happening with such frequency. Oh, wait, it is. It's Duracells. Never mind. It's just a relabeled Duracell battery. Here I was complaining about the batteries. Test. Boom. All right. So, recursion. So recall that recursion is the calling of a function by itself, right? We generally focused on numerical examples of recursion, but it's also possible to operate recursively over data structures. So, just as a quick example, let me just so let's say, for example, very quickly, you wanted to take the product of all elements of a list. We can do that with a loop fairly easily. We can also do that with recursion. So, def recursive product of a list. If L is equal to an empty list, return 1, otherwise return L at 0 multiplied by the recursive product of L from 1 until the end of the list. So, and let me just, a question?
Shouldn't there be two base cases? Because if the list is empty, how is the product 1?
Well, you've got me. So what I've done here is I've selected 1 as the return result for the empty list, because if we did calculate the thing all the way down, this 1 it'll disappear into the multiplication. That does mean, however, that if we're attempting to calculate the recursive product of an empty list, then, it does, 1 will be returned as the result, which is technically not probably what you want. I was trying to keep it simple, but we can make it more complicated. Let me prove this works first, though. So, let's say Q is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Print recursive product Q. Bing, bang, boom. Let me just run this bad boy. Python 3 review sesh. There you go. Right? And if you want, you can verify that with a calculator. So, the question, so basic, the structure of this guy, right? The structure of pretty much all recursion that you would see at this level, at least. We have a base case. We have a recursive case. The base case is what activates when the recursion is done, right? When you have reached the final state. The recursive case is what gets you there, right? So in this case, what we're doing, so long as the list isn't empty, we take the first element of the list, right? We extract it using the indexing operation. We multiply that against whatever the result of a recursive call to the same function will be on the entirety of the list without the first, without element 0, right? That's what this slice operation produces, right? Does that make sense? So, so let's say, just for the sake of interest, that rather than returning 1, we want to raise a value error here, right? That might be more toward what you would be interested in seeing from something like that, right? If you're trying to take the product of an empty list, you know, obviously that doesn't exist, so value error might be what you're interested in. So, since we're raising a value error here, which might occur when we call recursive product, what we have to do to catch that error if it happens, and it will happen because we have guaranteed it will happen by making it the base case of the recursion, we say try, there we go, except value error, then return L at 0 without the rest. So essentially what this will do, it will attempt to calculate this function using the rest of the list. If the rest of the list is empty, this will raise a value error. We will jump immediately to the value error case. Rather than attempting the recursion, we simply return the head element, which is also the last remaining element. That gets passed back up the chain, right? Multiplied against all of the other previous elements, and there you go. Bing, bang, boom. Just to demonstrate that this works, I will run it, and there you go. Wait, I need to save it. Save. There we go. Same result. So that would be a way of doing this that would be more in accordance with, you know, the thing always giving correct answers, if that makes sense. Good. Is that a sufficient review of recursion, or would you like to see something else? One more example? Sure. Let's say you have a, it's so hard to come up with on the spot. Okay. Numerical example. Def, recursive, thing. Who knows? Take some number n. Oh, I know what I'll do. I'll do the 3-place Fibonacci thing. So, Fib3. If n is equal to 0, or n is equal to 1, or n is equal to 2, then return 1. Otherwise, return, I'm going to just call it Fib3 because that's easier. Fib3 at n minus 1, fib plus Fib3 n minus 2 plus Fib3 n minus 3. Right? So, whereas the regular Fibonacci sequence is the sum of the 2 preceding entries in the list and starts with 1 and 1, this one is the sum of the 3 preceding elements in the list where 0, 1, or 2 all yield 1. Make sense? Question?
Will we be tested on memoization?
Memoization?
Yeah, memoization.
It's fair game, shall we say. So let's memoize this thing quickly.
Okay.
So first of all, what is memoization and why do we use it? Memoization is the storage of intermediate results of long calculations like this, which can become inefficient if you have to recalculate values a lot. So if you all recall from the course when we talked about the regular Fibonacci sequence, each one of these calls will generate at most 2 additional calls to Fibonacci. In this case, each call to Fib3 will create at most 3 additional calls to Fibonacci. So rather than being in a big O 2 to the power of n situation, we are in a big O 3 to the power of n situation, which is even worse, somehow. So, memoizing it. So in order to memoize it, you have to carry the memo through the calculation. So it must be an argument. Maintain compatibility with other versions that do not require a memo, or, in order to not break the code, you can include the memo as a default argument so that if it's just called regularly, it by default creates an empty dictionary. In the first case, we don't really care. In the second case, what we want to do is we want to test to see if any of these guys are in the dictionary. If they are, we use the dictionary value, and if they're not, we put it in the dictionary, and then we use the dictionary value. So, in all cases, we have memo at n minus 1 plus memo at n minus 2 plus memo at n minus 3. There we go. Now we just have to populate the memo. If n not in memo, remember that the in operation searches the keys of the dictionary, not the values, then memo, n minus 1, then memo at n minus 1 is equal to Fib3 n minus 1. We then just take that and we copy paste a couple of times. We make a few copies. There we go. Substitute the 1s for the 2s in this case. Substitute the 1s for 3s in this case. And there you go. The memo has, except I have inverted the indentation on the if statements, which is a silly mistake to make. There we go. Memoization complete. Except for the fact that I forgot to add the memo recursively, which I will do now. Done. Memoization example. Good. I'm going to say recursion is done. So, now let's talk about floating point numbers. Floating point numbers and floating point accuracy. Did you have a specific problem in mind?
Yeah, I had a question.
Okay.
I've got a question.
Speak.
So I've got a coding question.
Oh. You're not like, this isn't like you want me to go over the topic again?
No,
You've got, like, a
like
specific
how
problem.
would that specifically apply to that question?
That might be better suited for office hours, which you can come see me after class, after the tutorial, and we'll take a look at your specific solution.
Okay.
Right?
Maybe a more general question is to make it the most accurate as we can. Is the import decimal library fine, or is there any alternative approach?
So it depends on the type of number that you're storing, right? If the number can be represented using a fraction, fractions have sort of absolute decimal accuracy. You know, like 1/3 is absolutely 1/3, whereas a decimal can only ever approximate 1/3, right? So if you're in a situation where you can use a fraction, that would work as well. To answer your question about like holding the number of digits, the decimal library will hold more digits more accurately than native floating point representation.
Okay.
Make sense?
Yeah.
Okay. In that case, there we go. So, let's see here. Next would be object-oriented programming. So we wanted to go over the concept of self. So, I'm just going to bring up our examples from topic 8 so that we can see an example of it in the wild. So let's return to the birthday counter from previously in this course. You may note when we declare methods inside of classes, the first argument of each method is quote-unquote self. You can see that my editor expects that as a keyword because it's been highlighted in blue each time, right? In the same way that init has been highlighted, like the function names are highlighted, right? Self is a sort of designated keyword. Now it turns out that this is only by convention. There's no actual firm restriction requiring that first argument to be called self. You can call it Toledo or Baby Bunting or anything else, and it would still work so long as you were consistent. However, calling it self is conventional. So what the heck does it mean? Self always refers to the object on which the method is being called. So recall that these things basically don't get called in the absence of an object on which they're being called, right? Classes must be instantiated as objects in order for you to use these methods, right? The idea is there's no such thing as adding something to a birthday calendar in the absence of a birthday calendar. It doesn't exist. It's not an operation, right? So, self is self-referential, right? It refers to the object that the method has been invoked on. So, if we scroll down a bit, we construct the object in the regular fashion. Cal.add Nick and then my birthday. Cal is mapped to self. Nick to name, this date to the date, right? Now, it's also possible to provide the object inside of the argument list itself. If you do that, then it looks precisely like the way that the method has been written inside of the class itself. But in order to do that, you have to tell Python which class that method is coming from. So, essentially, cal.add me question mark is exactly equivalent to bday.add cal me question mark. There you go. These are alternative formulations. They can sometimes be useful. Note here, it is possible to invoke the constructor of the point class directly by referencing the class directly, and you then pop self and all of the relevant details over you pass it into a sub-construction. So, cal is self, me is name, question mark is question mark. And this tells you what class. Now, if it's an instantiated object, in this form, which class this is already known from the object, right? Here, it's not necessarily. Technically speaking, because Python is Python and Python is very loose with this sort of thing, you could pass in an object that isn't even a birthday object. If it had like similar operations, it would do them. It's like very terrible and in violation of many of the good principles of object-oriented programming, but whatever. But yeah, so does that make sense?
I have a question concerning the triangle depth there. Why do you need to assign self.a to
Good question. So, that's the other half of how self works, right? So, within a class, or within a method of class, I think I have an example of this a little further down, actually. Maybe further up. Let me see here. I think I've got an example. I must have an example of it. Here we go. So, what's the difference between dz and dx and self.x inside of this method? Answer. Dx is bound to the scope of the method, right? Dx only exists so long as the method is being executed. When the method ceases to be executed, it is destroyed in the same way that any local variable of any function is, right? Whereas, if you have bound the variable to the scope of the class by saying self.x, it is preserved. No. Private and public is different. Private means that it can't be accessed from outside of the class. So, you know, if I were down here, I couldn't say like self.x is equal to 3. That would be disallowed if x was private. If x is public, then that's permitted, right? No, this is scoping rules, right? So the class is a scope, right? Inside of that scope exists all of these methods and all of the variables that have been bound to the scope of the class using self dot, right? But if you have local variables in there, they function basically in the exact same manner as local variables of functions. In the same way that effectively, you know, self.x doesn't exist outside of the class. Like you couldn't just say x down here. It has to be bound to a class. Does that make sense? Good. Excellent questions. Any other questions about object-oriented? Yes.
So when we use other, like it's an instance of self?
It's another object of the same class.
So it's like self just duplicated for another class.
That's like not my favorite way of phrasing it, but you're like 3/4 to correct there. So other is conventional. Like again, you don't have to call it other, right? But other is conventional for another class, or sorry, another object of the same class. So like for example, down here, I have points A and B, right? If I were to call A dot distance B, A would be self, B would be other. So when I say other.x, other.y, other.z, I'm talking about the other point.
Got it. Okay.
Make sense?
Yeah.
Cool. Good questions. Any other questions? Yes.
Sometimes classes
You mean here? Oh yeah, that just means empty. Yeah. Generally, there's no harm in including the parentheses. Some people omit things for, you know, speed, but you may notice that when I program for you guys, I include all of the braces and, you know, technically a lot of brackets that aren't strictly necessary I'll put in anyways, either because they're necessary in other languages and I expect you to be able to program in other languages, or just because, you know, I think it looks neater. For example, this pair of brackets right here is redundant in Python. You don't have to include it, but I do. If that makes sense. You'll thank me when you take C programming. Any other questions about classes? No? Okay, good. All right, so technically speaking, that means we're on to file I/O. So, yeah. So, file input and output. I think that a lot of the so let me ask you guys a question. the difficulty that you're having with file I/O, is that in the reading of the files, or is that in working with the files once you've read them?
So, can I answer that?
Yeah.
So, it's like reading and closing the file is okay.
Yeah.
But modifying it, the in-between part, finding what to do with the information we have,
Yeah.
that's where it's a bit icky.
Yeah. So the problem with file I/O, like, is that shared sentiment between you guys? Yeah. Yeah. Like the opening, the actual opening, and the reading and the writing. That's not necessarily the hard part, right? What file I/O really means then is working with higher dimensional data structures, right? Working with, like, lists of lists, dictionaries with nested dictionaries and nested dictionaries in them, that sort of thing, right? Yeah, so it really helps to draw them, if it's a list of lists or a list of tuples or something like that. It really helps to take a piece of scrap paper and draw out what the thing is supposed to look like. Be aware of, the differences between looping through things and, getting at things by index. Generally speaking, if you're working with a dictionary, the thing that you want to do is you want to find the key that you're looking for by actually reading an example file, or possibly the question. It'll be in both places, but yeah. So like this example where I was processing the I think this one that's up here is processing the no, not quite. This is removing blank lines. I think it was in the JSON example, which was not too bad. Yeah. So, if you remember, the way that I came to this, the way that I got here was to look at the actual file, see what the tags are, right? And then just step through those tags, right? That's kind of the first step. Yeah. And it's maybe a little confusing because it's fairly compact here. But one thing that you could do is you could, if you want to get if you want to get the key of a dictionary, or get the value at a particular key, like for example, the list of cells, you could copy a reference to it to a variable and then work with that variable. That might make more sense, rather than having big long things like this. Basically, the further you get down this structure, the longer the list of addresses is going to get, right? Yeah. Does that kind of make sense? Another really useful and important a way that you can do this in a practical sense. It takes a little long to do this, but it's more likely to end up being correct. Every time you make a decision about a branch to walk down, print it. Make sure that the branch you're walking down actually contains what you think it contains. Because you can have this theoretical impression of where you are inside of the data structure, and if where you think you are isn't actually where you are, you'll have written all of this and it'll all be crap because you made a mistake back here, and it just doesn't work at all, and you're like, I don't know, this doesn't work at all, what do I do? And it's because, well, you have to tear it back to the first decision that you made about where to go through data structure. So yeah. Generally speaking, like I think this is primarily a problem of JSONs rather than, like, you guys are okay with CSV files and processing them? No? Well, the thing about a CSV file, because it's a collection of entries, you know at the top level you're always going to be doing a loop through them, right? Yeah.
Yeah, in CSV you'll always loop, but
Yeah.
because in JSON it's always in dictionaries, the output, so you need to think in terms of the data structures,
Yeah.
right?
Yeah, well, in both cases you're thinking in terms of the data structure. But, you know, with a CSV file, you know, basically it'll be something of the form, you know, do something for all of these data, right? Like, you know, maybe you want to, you know, you know, extract some information. One question, a question that's on, a practice question that's on the Avenue. I'm going to sneeze. Pardon me. I give a list of, like, words, and then you have to calculate a funniness score that's like some, you know, some calculation on the other values that are included in the CSV file, right? And so once you have a single entry, right, all you do is calculate the formula, and then after that it's just a max problem, like find the maximum of all these calculated formulas. You know, you don't even have to go to the trouble of saving them all in a separate list. All you have to do is, like, as you're going through, keep track of whatever the current maximum is, and by the time you're to the end, that's the maximum, right? All you have to do is keep track, which saves memory. But yeah, I don't know. You guys have any more specific comments or questions about data structures? Because, like, working with data structures is really, like, there's only so much theoretical help I can give you. Unfortunately, like, it comes down to practicing them, you know, and, like, working with them, getting familiar with them, and that sort of thing. And all, like, use the aids available, try to draw them, you know. Drawing a picture helps almost always. Print. Test early, test often, right? It can sometimes be difficult to visualize what JSON data is supposed to look like when it's all in a complete mess. You know, if you've printed it without, you know, including the spaces and the tabs and such. Fortunately, if you use json.dumpS, then you can actually insert all of those tabs for the purposes of printing, not only for the purposes of file I/O. So you can use that to make it a little easier to read. Make sense? Question?
This is like a test question for efficiency. So let's say we are doing this and we add multiple print statements to check if we're doing it correctly. In the end, can we just leave them in?
Yep.
Right? Because we just need to return the thing that's just us.
Yeah, print statements don't matter.
Okay.
It's like, I would say, mildly discourteous to leave them in. But if you're in a time crunch on a test, then yeah.
If it helps, and then you, of course, on the exam.
Yeah, just leave them in. It's being graded by a machine anyway, and the machine doesn't care. So, yeah. It does care about input statements. because if you leave an input statement inside of your solution, then the whole grading process will pause to wait for input.
Yeah.
So please don't do that.
Yeah.
But otherwise it's fine. Yeah? Question?
So when you're dumping a file, you change the name of the file.
Here.
Yes, it's
Oh.
not out.
Yeah.
And how are we supposed to do that when we just got like a very, like, let's say we didn't actually have.
Very practical question. Very simple. It would just be x plus dot out. Concatenate. Remember that the file name itself is encoded as a string, so all of your string operations are still applicable. There you go. If you want to get the like just the name of the file without the file extension, you can do something like x dot split on dot
Yeah.
and then take the first element.
Mm-hmm.
And then if you did that and then appended like, you know, dot, you know, exe or whatever,
Mm-hmm.
this throws out the current file extension and adds .exe, right? Strings, data.
So we always add dot out.
No, just in this particular case, I decided to do that. I didn't want to overwrite the original file, so I wanted to modify the file name in some way so that the output file didn't destroy the original input file. So that's why I did it that way. That was an arbitrary choice. On an assignment or test, we will tell you what the output file name should be, because the auto grader will be looking for a file with a specific name.
Mm-hmm.
Make sense?
So you just added dot out just like that. Like you can name it anything, right?
Yeah,
Oh, okay.
yeah. Just a decision I made.
Okay.
Yeah. And it's just a decision that I make when I write a problem and give it to you. Like I have made an arbitrary decision about what you should name the file. If that makes sense. Fortunately, it's not a difficult decision. Any other questions about file I/O?
So we will be tested on YAML, JSON, CSV, and SQL.
You will be tested on a subset of those formats, yes.
Okay.
The test isn't long enough to be able to test you on all of them.
No, definitely. Like, but you must know.
Yes, yeah, I'm not going to exclude one of those as
Yeah.
being, you know.
Of course.
Yeah. Yeah. Good. Any other questions about file I/O? All right. So, we find ourselves back where we were yesterday with SQL. So, SQL then. So, in practical terms, the means by which you access an SQL database from Python is a little bit more complicated than if you were to do a CSV file, for example. It is of absolutely critical importance that you import the SQLite 3 library. Then you create a database object by connecting to a file. Connect to a file. because this is databasing, and databasing likes to think of itself as occurring over a network, it's like, you know, connect to a network file is like the terminology it's using. But in our case, it's just opening a file, right? It's opening a local database, .db database file. Which, by the way, is binary encoded, so you can't view the file in any other way. If you include the next line, db row factory is equal to sqlite3.row, that allows you to use dictionaries to get at the particular elements of the entries in the dictionary, which could be convenient because, you know, that's kind of how SQL works in the first place. You know, you get at the fields by field name. The next thing you do is you open up a cursor. Cursor is equal to database.cursor. The cursor is the same as the little blinking box cursor in the SQL terminal that I was, you know, using quite a lot while we were doing this. But essentially, you should think of that as your port. That is your input-output port for accessing the database. You put commands into the cursor, you get results out of the cursor. Make sense? So once you have a cursor, the way that you execute SQL commands is to formulate them as a string and then pass them into the execute command. Don't worry about the question marks. That's like for inserting stuff. Don't worry about that too much. I'm reasonably certain we're not going to require your code to be, you know, not vulnerable to SQL injection attached. So just write regular SQL queries, right? So we can review the commands once we've talked about the process. So once you have executed the command, commands basically come in two flavors, right? They are commands that change values in the database, or commands that read values from the database. If it changes values in the database, generally speaking, there will be nothing to report, nothing to return, right? There's no data that's being given back to you. So you can just do it and not worry about the return value. If you have performed something like a select command to extract data from the database, that data will be stored either in the cursor object itself, where you can use fetch methods to get at it, as given in the slides, or you can assign the return value of that cursor object to a secondary variable. That variable can then be for looped over, and you can get the data. Once you have the data, then you do whatever it is you need to do with the data and return the result with the rest of the program. And always remember to save it with commit if you've modified it, and close it with close once you're done. Question?
Can we use with open with SQL?
No.
But Manav did it yesterday.
Oh, did he?
Yeah.
Oh, it probably links to this, but
I think he used this concept.
with close?
He didn't write db commit and db close. He just did with open. When you use db is equal to, he did with open SQLite. So
he didn't use SQL.like3.connect?
no, he used that, but before that he wrote with open, and he didn't have to close any.
Oh,
Yeah, I think so. Yeah, he did it like that.
okay. Well, you know, that works too then, I guess.
And one more.
One of the things about like programming is that there is like 100,000 ways to do any particular thing, so it doesn't surprise me that that's possible. I've been finding that lately that like I'm going to tell you like the one way to do it so that you have one way to think about, you know. But you know, you had another question?
Yeah. Do we need to know all of the SQL queries, or like update, delete? and what was it like? Like
Not
those.
generally. Generally, if you know insert and select, then that will be mostly sufficient.
So the ones that were in the lecture might be like
Like the
open.
quick fire round of like, you know, delete table and all of that.
Like I know it, but
Yeah,
okay, it's fine. Like
yeah.
only two. So.
Yeah, no, for sure, no select. Right? Select, I've never put a SQL problem on a test that has not required select. Make sense?
Good.
Good.
Also, Manav used with open for the cursor as well.
Huh. Interesting.
Now that I found very surprising, because yesterday you mentioned there was an error in the slides which said it's not cursor.com, it's database.com.
Yeah.
So then I was wondering, the cursor isn't being closed, the database, what's the difference between commit and close?
Well, commit is a save operation and
Close just shuts down.
shuts it down. And
Okay.
presumably any cursors that are left over would be shut down as well.
Okay.
Yeah.
Well. Multiple approaches work. So.
Yeah, exactly.
I think we have a tutorial today for SQL queries.
I think so.
Yeah.
Maybe. I'd have to check.
Because yesterday was SQL database.
Yes. Yeah, I think I remember him saying that too. Yeah. So bring your questions. It's like this. It's a review session. Yeah, we don't have. Yeah. It's kind of interesting because in the we kind of get the tutorials get offset because the first week there's no tutorials, but that means we lose 2 tutorials at the beginning of the semester rather than 1 because it's a summer course. So, you know, the tutorials get a little mangled during the summer, but yeah. Question? The which? Filters? Oh, yeah, sure. Yeah. So in concept, what a filter is it's a program that takes a set of data and eliminates certain pieces of data inside of that set of data that don't meet a certain condition, right? So, you know, if I had 1, 2, 3, 4, and I wanted to filter this data for all of those things that are less than 4, my filtered data would be 1, 2, 3, right? Make sense? With respect to that specific problem in the assignment, though, right? Yeah, so essentially what you would do, access the list that you're filtering, right? A good idea would probably be to, you know, build up a secondary list from those elements that would pass the filter, and then replace that list with the filtered list after you've generated it, right? Does that make sense? Yeah. Question? No? So let's just go through quickly the SQL queries then to review. I'm just going to pull it off the slides in this case. Because that's easy. So first of all, the way the insert works. Keywords, insert into. You select the table that you're inserting things into. And then alternatively, you can either provide the list of field names and then values, a list of values, or you could, if you're using all of the field names, then just say values and put that in there. Finish with a semicolon, right? With select, all select commands are views of the database, right? If you're selecting star, that means show me all fields of this table, whichever table is specified, right? So what you want to see and where you want to see it from. The where clause is a filter. It says, I want to see these fields from this table when those entries meet this condition. Right? So where genre equals comedy will show only those entries where the genre is equal to comedy. You can also have fuzzy matching if instead of the equal sign you use the word like and you use percent sign characters inside of the string itself. These are patterns that will match many characters. So the set of characters comedy will need to appear somewhere in the string denoting the genre, but its position doesn't matter because it has, some number of characters before and some number of characters after, including 0 characters. Does that make sense? You can also sort this in ascending or descending order. And in order to view data from multiple tables at once, using an inner join command, it's important not only to list multiple tables, but to restrict the view to, for example, instances where the customer ID is, where values in one table are equal to values in another table. Like matching primary keys is a good example, right? Does that make sense? Any questions about any of that? Yes. Yes, and call it, you feed it into the execute command of the cursor. Yeah. Yeah, just open quotes, close quotes, feed it into execute. Question?
So you just write cur.execute bracket and then in string.
Yeah, but don't forget the quotes.
String.
Yeah. And then close bracket at the end, and there you go. Yeah. Because this is a different language. This is not Python.
This is
SQL.
Yeah.
Make sense?
Yep.
Any other questions? Any other questions in general?
Okay, I have a question in object-oriented. So, when you write, let's say, class shape. Yeah, the class colored points, right?
Yeah.
And then you put it, and inside the bracket you put points. Why do you do that? I'm like, do you call back point?
Are you talking about right here?
Yeah. Exactly.
This designates point as the class that colored point is inheriting from.
Yes. Oh, yeah. Inheritance. Yeah.
Yeah,
Now
this
I-
is inheritance.
Mhm.
So, colored point derives all of the methods and attributes defined in point by default. Anything that it needs to update, it will provide a new definition for inside of itself. So, for example, point already has a definition for string conversion, right? So we create a new definition for string conversion, overriding the old one, right? And we can also use the old one inside,
Okay.
right?
Okay.
So yeah, so this is inheritance.
So it's basically like you're taking the previous version and using the new class and updating to the previous version.
Yeah,
Okay.
it's like the way that you're supposed to think about it is that you're making a more specific version of the other thing. So a colored point is a more specific type of point.
Yeah,
right?
definitely.
Yeah,
Yeah, got it.
awesome. Any other questions? Well, if all questions have been answered, then thank you for taking this course. I know it has been, trying at times, but it's been good. Yeah. All right. Incidentally, I'm currently leaning towards you guys having a crib sheet on the exam rather than like just copies of all the notes, if that makes sense. You guys have thoughts on that?
Like, okay, should I put it? Like, can we have a sheet or like few pages of the file opens, the SQL queries?
Well, if it's a crib sheet, then you get to decide what you put on it. So if you
Yeah,
want,
so
yeah.
like, but would it be only one sheet?
Well, one sheet double-sided.
Double-sided, okay.
Yeah.
So we can put anything we like on it.
Yeah,
Anything.
yeah.
Okay.
But it has to be on a piece of paper.
Yeah.
Yeah.
Definitely like physical.
Yes, definitely physical, yeah.
But that's it, nothing else. No Google, no nothing.
No Google, no Stack Overflow, yeah.
No slides.
Well, that would be the thing. That would be no slides, but a crib sheet. I think that the slides weren't helpful as
I
helpful
agree.
as people think they
I
were.
agree,
You know, I think it's like
It takes like it reduces your your self dependency goes down on yourself.
that. Yeah, it also takes a long time to flip through those slides
Definitely.
to find the particular thing that you want. And when you find the particular thing you want, I think this happened a lot on the midterm. It's not even the thing you think it is. Right? It's like you find an example of code in the slides and you just use it directly, you're not going to get any marks, basically, most of the time. So, so I'm thinking that we are going to move it to a crib sheet model where your job, your studying job between now and Friday, is to go through the notes and find anything that you think would be, something that you don't want to memorize, basically. Like specifically how functions are called, specifically how the file I/O functions are called, that sort of thing would be excellent crib sheet material. And you put it together and you bring it to the exam, and that's probably much better reference than the slides themselves. Although the slides can be very good, but not all of them for sure. Yes? Nope. You would have to use, no, you can't, no, there's no option. It's just a crib sheet.
as an assignment?
if you put it on your crib sheet. Yeah.
You couldn't do that last time, could you?
No,
Assignment?
not really.
No.
Yeah, like, Yeah.
So basically, you'll have just Jupyter Hub
yeah,
and crib sheet. That's it.
yeah.
And do it
Mhm.
in 2.5 hours.
Yeah.
Sounds simple.
Sounds impossible? Well, that's what we do. This is our species. We do impossible things. Yeah. Yeah, I think we're done. Okay.